Okay, so I'm actually going to be talking about more on the application side. So Catherine kind of gave us all the hardware and the new OpenMP 4.5 constructs that she showed. So I'm going to give you an application side view of what problems we had or what successes we had using some of the OpenMP 4.5 constructs. So as Shavi mentioned, there's not a typo. Vivek actually moved, so a lot of you might know Vivek, and he was at Rice. He recently moved to Georgia Tech, so it's not a typo up there. So we moved, basically. Okay, so the application that we're talking about today is DRMG++. It's a physics application written based solely at Oak Ridge National Lab. I'm going to talk about the application briefly, not getting into the physics details. But this talk, mostly what we're trying to get from the audience here is we have done stuff with using OpenMP, but we want to know what we could have done better using OpenMP, and I'm going to show the challenges we faced. So if you think that you have a better solution, we are all ears, basically. So as we all know, that the data centers and the Oak Ridge, the OLCF machines, or all the next Exascale machines, the architecture is becoming more complex. It's hybrid in nature, so you have a lot of heterogeneous cores and architectures in each of these machines. And what we feel like the applications at these labs need to kind of adapt to the hardware itself to get performance out of even using OpenMP or MPI as well. So what we're doing is it's a standard approach at a lot of labs is design mini applications out of the original application, extract the most time-consuming kernels, and then use that so it basically serves as a foundation for Exascale-ready implementation. And we're also co-designing this application with other programming, asynchronous programming models like Habanero C++, Cocos, and Magma. Although I'm not going to be presenting anything with Cocos and Magma, I'll show briefly about what we did with Habanero C++ as well. So kind of the outline of the talk, I'm going to talk about the application briefly, followed by what the motivation is, which is kind of twofold. There's a physics motivation, and there's also a programming languages models motivation for us. And then we'll talk about the mini application, the kind of design implementation, and I'll talk about 3 different program styles in OpenMP that we used, and each challenges we faced and why we moved on to the next style. And followed by some of the programming support that we currently have, and we'll end with some future OpenMP constructs that might be added, which I'm not sure whether, because we know that it's already OpenMP is pretty large, that's what everyone's saying, but let's see if we can convince to change a few things. Okay. So the DRMG++ is a physics application. What it does, it's a density matrix renormalization group. Basically what we need to know is it helps you understand nanoparticles, I would say it's more like the heat, how much heat is generated from these nanoparticles. That's what you get from the application itself. It's a sparse matrix algebra computational motif. It's not a general sparse matrix, so it's composed of smaller, dense, and sparse matrices inside each matrix cell, which I'll be talking about later. It'll make more sense there. And this is not an application that's done sitting there. It's actually an ongoing application, ongoing effort that physics folks are still working on at the lab. So to start with, what we ended up doing is we had a shared memory DRMG++. When I say shared memory, it was not even written in C or C++. It was actually MATLAB, and then there's some Fortran F90 code as well. What we did is we used OpenMP as an outer kernel, programming model to just call this kernel. We used 8 threads on the Titan node to call this kernel. What you see on your right is basically the application that runs in phases. So the application, what happens is it runs in 5 phases, at least for this data set. it can go up to like 10, 15 phases, but what I'm showing you is 5 phases, and each phase basically does a similar kind of computation. So it's all the same computation. What changes is the data size actually changes. So the matrix basically changes as we go from pH1 to pH5, and it's a convergence algorithm, so it continues till it converges to the point where the physics folks need it to converge. And what we see here is this, we plotted standard deviation over index of instances. What we're seeing here is as the data size increases, your sparsity, it's more dispersed, not sparsity. It's more dispersed, so what we see is there's more load imbalance once we increase the matrix that we are trying to compute. And since it's a dynamic application, so over time, your load imbalance kind of keeps increasing. And so that was one of the reasons that we wanted to use OpenMP tasking to kind of attack this problem in the first place. So as I mentioned, the motivation is kind of twofold, both physics and programming models. For physics, currently the DRMG++ only works on one-dimensional problems. That's what they're working on. So scaling this up to pre-exascale models will help them actually solve a lot of two-dimensional and three-dimensional problems, such as like semiconductors, power grids, and also work on first principle models without, currently they approximate the electron-electron interaction, which they'll not be doing, and they can actually put in those values because this takes up a lot of resource that's currently not available using the shared memory implementation that they have. For the programming models, folks, what we are more interested in is using OpenMP in a more, I'll be talking why nested parallelism. We tried to use OpenMP tasks as well, so task loops, new construct that we get support in 4.5. And so, as I mentioned, it's a co-design project. We are also exploring task-based programming models, which can also be a candidate for future OpenMP extensions. And we want to look at what programming model kind of fits in and gives us more productivity, but at the same time not hampering the performance. And we're also looking at a couple of compiler optimizations that I'll be talking about. So let's look at the execution model briefly. So as I mentioned, it was an 80% time-consuming part was actually calculating the sparse matrix Hamiltonian. What is a Hamiltonian matrix? I'm going to come in the next slide. It's a two-dimensional dense sparse matrix, and we used 3 different programming styles that I'll talk about. Nested parallelism, we moved on to multi-level tasking, and then multi-level tasking with nested parallelism. So this is the basic kernel that we'll be looking at throughout the entire talk. So it's y equals h times x, where h is basically a Hamiltonian matrix. And this is an interesting matrix, so that's why I kind of pointed out how the matrix looks like. So we call it CIJ. It's a two-dimensional matrix, looks pretty standard two-dimensional matrix. The end patches actually comes from a previous application that feeds in as an input. Now each cell in CIJ will actually have 2 matrices, 2 vectors, one-dimensional vectors of size k, where k is also predetermined. It's usually 4 for our case. But so what we see that is both A's and B's will have the same size, but it's not true that all cells in CIJ will have the same density of A's and B's. So you'll have the same size, but it's not dense or sparse. So we need to figure out what the density of the matrix is before we start multiplying, because that will affect the performance as well. So merging those two, what we'll have is basically a CIJ matrix, or like a Hamiltonian matrix here, and you'll be doing a product with the x vector that gives you y. So x is also feeds in from as an input from a previous application, from a different application. So the sequential kernel kind of looks like this. So as you would expect, that there's a two-dimensional matrix multiplication, so you would go C rows and C calls, and then you have this is where the A's and B's, we extract the A's and B's because there's a vector inside each, and there's a dgem call. We currently use an IBM ESSL to actually do the multiplication there. And something to note will be is that there are codes in between as well. So we dereference the value of j, and we have codes in between. So we have no luck with collapsing. Eventually, when I'll talk about nesting, we don't have any luck with collapsing there. Now, so the parallel part kind of comes out pretty easy from the previous slide. So the first one is a parallel 4, and then we have 2 reduction operations in j and then in k. So we have 2 reduce operations and one a standard parallel 4 that will just copy in values, so you don't have a reduction in that level. So 3 different programming styles and problems or successes of each, and then we move on to the next one. So let's look at the first is the nested parallelism. So what we have is OMP parallel 4, OMP parallel 4 with reduction, and OMP parallel 4 with reduction as well. So there's 3 OpenMP constructs here. Those are user-defined reductions because we have STL vectors, and we cannot have a standard reduction, so we actually wrote our own user-defined reduction. It's a standard, it's an addition operation, but you still need a user-defined reduction there. So this is what the overall the code looks like, and there are more snippets of code here that is not quite relevant to the kernel, that's why I'm not mentioning here. But the issues of having this, I'm going to show in the performance what happened, but the problems the challenges that we faced is currently we don't have any support for nested work-sharing loops, so you cannot have like one OMP parallel region and then OMP4, OMP4, OMP4. It will not let you compile as well if you end up doing it that way. So you need OMP parallel 4, OMP parallel 4. So you're creating and destroying parallel regions every time. And this is implementation centric, the creation and destroying, but we kind of tried with XLC, GCC, and Clang++, and all of them gave us the same issue basically with creation and destruction of these parallel regions. And currently I think we were looking for some support within these work-sharing loops to debug code, and this is also an open question that we couldn't find anything that OpenMP supports at this point to have like a OMP single or a master to not let you call anything within work-sharing loops. So you cannot like print statements or like debug using any OpenMP constructs. I thought you no, okay.
Did you try the IBM?
Yeah, we did Excel. So, oh, okay, no.
The one that you talked about, the oral. When you say Clang++, there, I think that's what we refer to.
Yeah.
Did you say you can't put print statements?
You can, but you cannot have a critical region or a single or OMP master.
You're going to print?
Within, so work-sharing loops, if you have nested work-sharing loops.
Right?
Now I'm looking at, it can be implementation centric, but we tried, it did not let us compile as well. Yeah, okay. And so this is an issue that we had with thread affinity, mostly at depth 3. Till depth 2, it's okay. So even if you use OMP places and prog bind, so you do like a spread and then you want to keep it inside that spread region, it would not hold when you go to depth 3. So we tried it with 3 different compilers, and it's implementation centric. It's different for different compilers, but it never stays within the spread region for the outermost parallel region.
It works on the Intel side.
Okay.
It works with Clang for the Intel.
Okay. Okay. Yeah. Yeah, so like GCC, it currently does not work. We show results as well. Okay. Yeah. 117. So no, sorry. We used the one on 1.7, right? Yeah. Yeah, so this is the latest version that we have on, so I'll be showing results on Summit Dev, and I think we have 1.7? What's GC6, yeah, so, yeah. Okay, yeah, so currently with 6, it doesn't work at that level. But yeah, with 2 levels, everybody kind of holds, so for every compiler. Oh, okay. that was not what I wanted to do. So we had issues with the performance because of that creation and destroying of parallel regions. So we were like, okay, let's try with task loops. It's a new construct, OpenMP 4.5. So what we ended up doing is using OMP task loops instead of OpenMP parallel force. So again, we have 3 levels OMP task loop, and then we have reductions. So as we all kind of know that currently task loops, we don't have any reduction support. So what we ended up have to do is you need to create a parallel region and then reduce in that parallel region, which kind of defeats the purpose because that's what we had in the first place. So it would be nice to have some task level reduction support. I know this is a common topic that has been there for a while, but yeah, so for us that was a major problem in the tasking. One more thing was nested task loops, and this we are kind of not sure because we did get some inputs from GCC, and so they let you compile. The spec doesn't say anything, if I'm not wrong, right? That task loops within task loops are allowed, so you can actually compile, but it will not give you the correct results based on different compilers actually give you different results.
What do you mean by different results?
So yeah, it's the wrong answer. So yeah, so even if you write the reduction correctly and you have those parallel regions, you would not get the same result. So what we feel like what happened is for task loops, certain implementations will create like a copy of like parallel task loops. So you'll have, if you have a task loop outside and you do a task loop inside, then it'll create that many number of task loops inside rather than breaking it up. So it doesn't become a task sharing loop anymore. It becomes like a parallel, like 5 iteration task loops. So, and this is true for I think Excel and GCC. Yes, both Excel and GCC. So at least 1.6.
Did you try just generating the task yourself?
Yes.
Recursion?
Right. Yeah. So you can create a task group, and then you create tasks. That's how you would get a task loop, and it works. Okay. Yeah. So the problem is currently with the implementation of task loop rather than the concept of tasks. Yeah. Okay.
And it's not a matter of the specification is insufficient. It doesn't have.
That's right, because right. So for the OMP parallel force or like the nested work sharing, the spec actually says that you cannot compile, whereas in the task loops it's not very.
It's not really that it should be. All it's doing is generating tasks.
Exactly. Yeah. So, and they also say that it's a task sharing loop, not a work sharing loop, so it should be pretty standard of, so yeah, it's not the spec, it's probably the implementation itself, yes. So as I mentioned, the lack of support for task level reductions, which makes it difficult for us at least in this. And this is the same thing, we had issues as well that you cannot add OMP constructs again inside task loops. We could not add OMP single. I'll check on the critical though, but I'm pretty sure that we couldn't add. Yes.
You cannot have single. You should be able to have master and critical.
So if you have 2, 3 levels, at the 3rd level when you do master, it will not let you compile. So, which can be totally implementation.
I mean, master just means
it's like one thread. Yeah.
First thread.
I'm sorry? Yeah. Yeah, sorry? Okay. And this is something that we kind of needed for our application or other physics applications that we have at the lab as well is currently tasks will let you map, like when you use grain size, you can map threads to tasks. So you can say that, okay, there will be one thread that can do 3 tasks or 4 tasks, but you cannot have something like one task doing 3 or 4, using 3 threads or 4 threads. So you cannot do the mapping the other way. And that's what we kind of needed is to change dynamically as well that let's say one task needs only 1 thread and then another task needs more resources because it's more compute intensive. So that at this point directly you cannot do it with an OMP construct. So because task loops did not work for us, that's why we ended up moving into tasking with nested parallelism. What we ended up doing is you create an OpenMP parallel region everywhere, and then we create OMP tasks, and then you reduce in the parallel region instead of reducing in the task loops. So that kind of comes back to the first programming style, that problem of creation and destroying of parallel regions. Now this is also interesting with task loops is the variables are first private, so reduction kind of becomes complicated to actually do it as well, because you kind of got to tweak the variable to make it thread private, and then you move in inside the task loops. Otherwise it will create like a copy, same copy of the same variable. So you want to make it thread private, and then you move in to do a reduction if you want to do a custom reduction. Same issues with task affinity at depth 3. So we couldn't find anything where it says that it works with depth 3. I'm not sure whether people have worked with 3 levels of nesting in other applications. But once you go to depth 3, even if you do tied tasks, it will not stay in the same region. So it will move away and go to a different core. And this is true for, I would say, GCC and Clang++. Yes. So we ended up using GCC, XLC++, and Clang++. I'm going to show results for GCC. We ran it on Summit Dev. This is a it's like one generation off in the OLCF machines for the new Summit. So it has 2 10-core IBM Power 8 processors with 8 hardware threads. So we're going to show with a total of 160 threads. There are GPUs. We did not use any target construct, so we're not showing any results on the GPUs. And the DGEM, the actual matrix multiplication, is done using IBM's ESSL, and we also tried a threaded version, the ESSL SMP. And IBM does say that you have to use XLC when you're using ESSL, otherwise they don't say whether it works or not, but it gives us the same performance stuff. So this is the data set. It's kind of interesting because what we have is that the matrix is not sparse or dense at a large scale, so all the data is kind of in the principal diagonal itself. And your density increases when you're moving towards the center, and your sparsity increases as you're moving away from the principal diagonal. So you have to be careful when, even if you're tiling this matrix, you still get spots where we don't actually need enough resources. So that's where the task elasticity comes into play, that we want task elasticity where we can change the resources dynamically as well. And as I mentioned before, with the different phases, even if the phases increase and the entire matrix increase, the pattern stays the same. So we'll have the same problem as we move forward with a bigger data set. So what we're showing here is the blue lines, so it's a speed up over the number of threads. We use 128 threads. We're parallelizing the I and that is J. I don't know if it's clear, but yeah. So each loop is parallelized separately here. So you have only parallelized I loop, and then we only parallelize J loop. What we're seeing here is a kind of slowdown because the J loop actually does the vector reduction. So whatever you see here is the overhead of doing the reduction itself in the J region. And we did not parallelize the K loop because we're using the DGEM kernel, and using the SMP mode, they will parallelize it by itself, which I'm going to talk about how they parallelize the ESSL. So this is the green lines are the projected graphs. What would happen if we did not have any overheads and we just did a product of I times J, whatever we got from the previous slide. And the blue lines are the actual nested parallel for I loop and J loop that we got using OpenMP. So we use outer spread and then inner close, and this is we use dynamic scheduling, and this is actually we did different scheduling, and this is the best one that we got, and that's what we are showing up here. So these percentages are what is the overhead over creation and destroying of the parallel regions. Basically, that's what we are showing in so that it's 52% off the green bar and 36% off the green bar. So it kind of increases, which is obvious as well, and kind of grows there. So what we see is a huge overhead of these creation and destruction of these parallel regions. Again, this can be implementation centric, but all three compilers, at least with the ones that we used, has the same performance results. So we also looked at how OpenMP kind of works into with other libraries that we are calling inside OpenMP. So for DGEM, for the IBM ESSL, what they state in their spec is you can have a single parallel region, and then you can have an IBM ESSL SMP version. They will not let, at least with the spec, you cannot have multiple parallel regions and also have a spec. I also have a ESSL SMP. You can have it. It will let you compile, but the behavior is not defined in the spec. So what we end up doing is you create one parallel region, and then you have a ESSL SMP. We have no other OpenMP constructs in between. So the way the current spec works, at least the current implementation works, is you set your number of threads using OMP set num threads. So there's nothing dynamic. You have to do it at the start of your program, and so you keep it whatever it is. And it's not, ESSL is not picking up like smartly, okay, there's enough work, we'll do more threads, or there's not enough work, we'll not do it. So if you specify number of threads as, let's say, 2, it will run with 2 threads, irrespective of the fact whether the work is enough or not. So the user kind of needs to know what to put here, and it's not dynamic as well, so you can't put different things for different locations as well. And so that's what I mean by the dynamic thread assignment. Let's see. And currently with OpenMP, we didn't find anything with respect to the construct to extract some task level or thread level information when we are inside the IBM ESSL kernel. They say that, okay, we are doing using 2 threads, but we don't get any information out from there. We can see it's doing because the performance goes down right away. And within the nested parallel region, according to the spec as well, it's undefined behavior. They don't say what it should be. Got about like 10 minutes? Yeah. Okay. So this is kind of an orthogonal work that we are also doing with the DRMG++. Habanero C++ is a programming model that's it was actually designed at Rice, but now we moved, so it's now Georgia Tech. And so it's a task-based programming model. It's kind of lightweight. It's a work stealing-based model. And so we say that, okay, we can use HClib as a path to Exascale by using, for the intra node, you would be still using OpenMP, and you'll be using like resource management, using Habanero C++ as a resource management tool. And when you're going to the inner node, you'll be using MPI, UPC++, and OpenSHMEM. And HC++ basically gives you the abstraction to work on it. So this is similar to reductions that we support at this point in Habanero C++. We call it finish accumulators. It's kind of an atomic operation. So there's 2 different implementations at this point. We have an eager operation, which is more portable, and what you end up doing is like you have 3 threads. Every thread can put 1 value in it or multiple values in it, and it accumulates here. Only once you go out of the end finish is basically similar to like an end of a parallel region. So when you go out of the parallel region, you can do a .get and you would get the values, and that's where the accumulation happens for the eager reduction. Sorry, oh my god. And there's a lazy reduction where we have values in different small containers, and your reduction only happens when you call the get. So it's better performance that way, so you're not accumulating every time, you're accumulating only once you need it. So this is a work in progress. What we can do is we can create one parallel region. We do not have to create multiple parallel regions. We can create one parallel region, and you can see we have OpenMP tasks here, and we'll give you the correct results using accumulators. So we created as a user-defined accumulator here. This is your type, so you can do sum, divide, anything basically there, as long as you define it. And this is where we're doing the update. So that's the only update operation that we have in the entire code, and you retrieve it at like when you finish the parallel region in 17. So you can do it currently using one parallel region. That's what we want to kind of show here. So to kind of wrap up, what we're thinking is some of the candidates that can be for future OpenMP support would be nice to have is support for task level reductions. The task inflation that we're talking about is like dynamic resource allocation. Task affinity, like extending of tied tasks to check like whether it can be totally implementation defined as well, but at the third level we saw that it's not, it doesn't hold true. The thread persistence, again in depth 3, it doesn't hold true as well. Currently we don't have support for dynamic OpenMP places. It's static, so you would create it outside when you're like calling the actual code, and once you start the kernel itself, you cannot change the OMP places as well, which we needed for a certain different kind of applications where the kernel itself is growing, so you want to change the OMP places there as well. And addressing debugging challenges would be something interesting for us as well. So just looking forward, what we are doing right now is we're using the target directives, which is kind of obvious, I guess. For the GPUs on Summit Dev. We're using OpenMP parallel regions, teams, to create abstractions on the CPU itself. So we're using teams, but we're using it on the CPU. So we're going to try that out. And we're co-designing with Cocos at Sandia, Magma, it's a UTK's DGEM kernel, and then Habana C++, with Georgia Tech and Rice. And yeah, the original was written for Habana Java, and then we moved it to Habana C++. So yeah, with that I'd like to thank our collaborators, mostly DOE, Oak Ridge National, and then Weil, Ed, Gonzalo, Oscar's here, Vivek, and we have a research scientist from Rice and Georgia Tech. So yeah, and with that I'll take any questions. Thank you. Yes.
So is AA a matrix?
I'm sorry? It's a vector, yes. It's a one-dimensional vector.
So where's the matrix multiplication from? Where's the DGEM from?
I'm sorry, I don't understand your question again. Let me pull up the...
dot bk dot x. For example, this one.
Right.
Where's the DGEM from?
Where's the DGEM from?
Yeah. You are calling matrix multiplication, so where are matrix?
So these are, so the CIJ, so that's what happened here. So that's your CIJ matrix. Does that make sense? So this is the two-dimensional matrix. So you're calling each cell, you're picking up one cell here and you're picking up certain values from here. That's what you're doing a product of.
Okay, fine.
Right?
I can ask it later.
Okay.
So keep back to your pseudocode. Apart from reduction between I and J loop, J and J loop, and is there any other thing?
Apart from reduction in between, like here? Yeah, so we have certain functions that need to be called, and we need values for that needs to go inside the parallel cable. Yeah.
But how much time you spend on the DGEM and how much time you spend on?
So the DGEM is like the 90% time for this.
So why don't you just because mainly the other thing is you doing reduction selective results. Why don't you just start a single OMP parallel, then have a local variable? Why? Then you do OMP for /read group and just recompute those small things
So if you have collapse 3, then you cannot actually, if I'm right, that you cannot have collapse 3 with stuff in between, right?
And then if it's more, just recompute.
Oh, okay. Okay, but we are still not using the concept of nested parallelism though, once you collapse. Yeah, so I think that was the point as well here, is like we are showing that we are using and what's happening, not rather than we already have we know that we can do it by changing the kernel itself. Yes, that is always possible. That is always true for all cases. But without changing the kernel, keeping it as it is, what we can do using the open. That's what we're showing, rather than changing the kernel.
My point is like, since it doesn't give performance anyway, those corner cases may not be the focus thing.
Sure, yeah. Yes. Sorry. Okay, sorry, yeah.
When you're looking for elastic tasks, you said, and it's not clear to me whether you really need the ability to devote more threads to individual tasks, or if you need support for the granularity of the tasks in these areas. Right? Because in the end, you're just trying to generate a task design.
Sure. Yeah, so what happens, like, for at least in this case, or like even in the cases that will grow, is you will be creating tasks for places that you don't even need it as well. So that's the granularity part. And now there are cases where you need more resources for each task.
So if you make those tasks, if you split them into more tasks, then you just get the resources. Is what I'm suggesting.
In this case, for the library core feature, just as a task, it is basically the point where we go from the task, parallelism, data parallelism, right?
Okay.
Yeah, so it's the tasking is more like the abstraction of this matrix, and then we call the data parallel, which is the DGEM kernel, and there we want more resource to be assigned to certain places, less resource, but that is not currently letting us do.
The fact that you're kind of mixing task parallel with data parallel.
Right. Yeah, I should have clarified that. Yes.
Have you given much thought to using more than one GPU device? How that would map to that parallel?
And the
outline that you had. Have you used multiple GPUs?
No, we have not. We have not. So yeah, we would be happy to get inputs on that. No, currently it's only one GPU, and then the breaking up of the computation itself is going to be challenging as well, because we can change the kernel totally to make it, because as I showed, that the data will kind of stay in the primary diagonal. So what you can have is divide up that primary diagonal into small batches and send it over. And then you can leave the upper triangular matrix and the lower triangular matrix as a sequential version as well. And it's not dependent, so you can do it totally orthogonally as well. So it will not be a problem. So.
Any other questions?
Yes.
A comment for the open of the nested team.
Nested teams? I did not use. Okay. Yeah.
The default behavior for some process that they create threads if you are going and destroy the thread after you
at the end. Yeah.
And did you experiment with the environment variables that fix this behavior?
Yeah. So even if you you cannot actually fix the behavior saying that don't destroy. You can spin the threads. You can spin the threads that are already created. You can actually call it and you can spin the threads. But you cannot actually say, oh, don't destroy the threads. It's totally implementation centric. At least that's what we figured out, is when you have multiple of these OpenMP parallel regions, it is creating and destroying, and that's what's causing the main problem.
So there is for the LVM and in the content there's a variable where you can set a level for nesting,
sure.
which the threads are capitalized.
Okay, we did not.
And then the runtime will use this thread pool and we use threads.
Okay, we did not try that. Yeah, we should talk about that. We did not try that. Yes.
Okay, let's send the speaker again.
Thank you.